All right, now let's look at the kind of transitions that we can observe in our experiment. The transitions that we're going to observe are absorption, meaning that the energy of the molecule will absorb a photon and go into an excited state. Okay? And in that transition, both quantum numbers can change. In principle, the vibrational quantum number could remain constant, or it could increase by 1. And the rotational quantum number could remain constant, or it could increase by 1, or it could decrease by 1. Okay? These are the possibilities. In fact, we won't see all of these transitions for the following reasons. Transitions where delta V equals 0, these are called pure rotational transitions. And we're not going to observe them in our experiment because in these transitions, the transition energy is so small that it's outside of the range of the equipment that we're using. Okay? Delta nu equals +1 transitions will be called rho vibrational transitions. And this is what we'll be observing today. In addition, there are 3 types of rho vibrational transitions, depending on how the rotational quantum number changes. It could change by +1, 0, or -1. And there's a nomenclature about this. Transitions where delta J is +1 are called R-branch transitions. Those in which the change is -1 are called P-branch. And those in which delta J is 0 are called Q-branch. For the molecules that we're going to observe today, for the particular transitions that we're going to focus on, the Q-branch transition turns out to be absent. So we'll see just R-branch and P-branch transitions, delta J equals +1 and -1. And in addition, we'll look at transitions where delta V is equal to +1. These are called rho vibrational optical transitions. One more thing. For our molecules, the energy spacing between vibrational states is much greater than kT, Boltzmann's constant, times the temperature at room temperature. And the meaning of this is that essentially all of our molecules, or nearly all of our molecules, start in the ground vibrational state. That means mu initial is equal to 0. All our transitions are from nu equals 0 to nu equals 1. On the other hand, this term, h bar squared over 2I, which is the order of the spacing between rotational states, and is sometimes called B, to give it a shorthand, this is less than, or the order of kT. And what that means is that many J states are occupied. So we can't assume that J equals 0 in the initial state. Oh, excuse me. Okay, let's draw a diagram showing the kind of transitions that we'll observe. And this ends up looking a little complicated, but if you understand this diagram, then you'll understand the analysis of the experiment we're going to do. Okay? So remember, we're going to start from states in which nu is equal to 0. Okay? And we'll make transitions to states in which nu is equal to 1. Okay? But both the vibrational and the rotational quantum number can change. Okay? So we need to include the rotational states as well. Like so. All right. And now we can draw in the kind of transitions that we're interested in. So for R branch transitions, delta J is +1. That means if we start at state 0, we'll make a transition to state 1. Or we might start at state 1 and make a transition to state 2, or start at state 3 and make it, or start at state 2 and make a transition to state 3. On the other hand, there's another set of lines called P-branch transitions. In P-branch transitions, delta J is -1. So there's no P-branch transition from J equals 0, but there is one from J equals 1. From J equals 1, we can make a transition to the J equals 0 state of the next vibrational band. From J equals 2, we could go to J equals 1. And from J equals 3, we would go to J equals 2. Those are the P-branch lines. Okay? Something you can see right away is that if we imagine the transition from 0 to 0, which would be a Q-branch transition, but not something we see, then all of the R-branch transitions are larger in energy than that. Whereas the P-branch transitions are all lower in energy than that. And in fact, remember that these transitions are going to be caused by absorbing a photon what this tells us is that we could expect to see absorption lines at certain energies. Okay? So we might see an absorption line at an energy slightly higher than h bar omega naught. Like so. Or we could see transitions at energies that are slightly lower than h bar omega naught. Okay? The ones on the low energy side would be the P branch lines, whereas the ones on the high energy side are the R branch lines. I remember it this way. If you draw a graph of transmission versus energy, the R branch lines are on the right. Okay? But I don't know why they're called P and R. You have to ask a chemist. So when we do our experiment, we expect to see a series of absorption lines that are going to be centered on the energy of the vibrational transition. And then they'll be spaced out from that point accordingly. Okay? So our next task is going to be to work out the energy for each of these lines.